Okay, so today we're starting S2 with our first lesson on correlation and regression. So remember, the exam is split up into 4 questions. You will have really one on each. The correlation and regression will cover, I think there are 4 lessons. So there are there's a few different types of question that can be asked based in this topic, okay? Which is unusual given the actual rest of the topics. So it kind of alternates a bit between the different topics as to which one it's going to be. So today we're going to be introduced to the product moment correlation coefficient, which is quite a long name for something that we use to do with scatter graphs, okay? So the scatter graph that you should end up with looks something like this, okay? So you might at GCSE automatically be thinking, right, I want to draw a line of best fit that goes with this data, okay? Hold off there, right? Line of best fit was always by eye, and one person could draw a completely different line of best fit to somebody else. They were always kind of fairly inaccurate ways of doing it. So part of what we're going to be doing with this series of lessons is really looking at, can we draw a perfect line of best fit? A line of best fit that will be the best line of best fit, effectively, right? So that's part of the process. We're also going to be considering, as we are today, looking at how correlated 2 bits of information are. So can we attribute a measurement to go with this data, which tells us how correlated it is, as compared with another graph? So what we need to first of all start thinking about is the difference between independent and dependent variables. So I don't know if you've covered this in other lessons before, other classes. Matt's nodding his head. Got a shout out there. Hold on. So what I'm going to do is I'm going to propose a couple of situations as to determining which is the independent and dependent variable. We're talking about really which one depends on the other. Okay? So we could say we have the number of people in a lift against the total weight of the passengers. So what you need to ask yourself is, does the total number of people in a lift depend on the total weight of the passengers, or does the total weight of the passengers depend on the number of people in the lift? Now, which way round sounds like the correct one? Second one? Hands up for second one. Hands up first one. Always the first one kind of like sounds really odd, to say that the number of people in a lift depends on the total weight of the passengers, okay? So here we would say that the total weight of the passengers depends on the number of people in a lift, okay? So we would put the number of people in a lift as the independent variable, the total weight of passengers as the dependent one. So it's kind of like the independent variable is kind of like one that we have somehow some kind of control over. That's not always the case, but if you have some kind of control over that variable, then usually that's the independent one. Let's try another one. The amount of rain falling on a field whilst the crop is growing versus the weight of the crop yielded. Right, have a think about that with the person next to you. Right, which one do you think is the independent variable? Which one's the dependent? Okay, what do we think? Weight of the crop, the dependent one? So the weight of the crop depends on the amount of rain that's fallen on the field. That sounds about right. The amount of rain that's fallen on the field surely doesn't depend on the weight of the crop. Okay? So it just doesn't make sense the other way round. So the weight of the crop yielded must be the dependent variable. Okay, one last one. Have a think about this together. Second one is independent. So the number of people visiting a bar in the evening depends on the volume of beer sold, or the volume of beer sold depends on the number of people visiting a bar in the evening. It's the second one, right? So as you say, so it's actually, this is the dependent one, that's the independent one, okay? Now, I said that maybe this one we have control over, that independent variable, but obviously here, the amount of rain falling, we don't have control over that, okay? But the number of people visiting a bar in the evening, we might have some control over that, okay? That idea of being able to control one of the variables isn't always the case of it being an independent variable, okay? And we might not have any physical way of controlling it. So back at GCSE, when you were doing scatter graphs, you were used to determining whether things were positively correlated, negatively correlated, or had no correlation. So in order to show that there is positive correlation, what is important to get across at this stage is that if the data is roughly elliptical, so that means I can draw an ellipse around the data like so, so it kind of like condenses it in that direction, so from bottom left to top right, then we would say that the data is positively correlated. The longer and thinner that ellipse is, the stronger the correlation. So this is an important note to write down, okay? This idea of being able to draw an ellipse around the data. Okay? So the data is roughly elliptical. Make a note of that, because that could be something important in the exam, right? As for negative correlation, in a similar way, the data can be collected, it seems, into this oval shape. Okay, now go from top left to bottom right. Now I said that the longer and thinner it gets, the closer the negative correlation gets to perfect negative correlation. So the more rounded it gets, okay, the less the correlation. Okay, the more it kind of represents kind of like a circle, the less the correlation there is. So we would say here that there is no correlation between the two variables. Now, what we need to be on the lookout for is sometimes data, when you plot it on a graph, looks correlated, but actually, with a little bit of thought, it probably actually isn't. So, for example, I could have this situation. So, two islands of data, effectively. What could this represent? It could be, I don't know, shoe size and height, okay, between some 4-year-olds, okay, and maybe some 18-year-olds. Right? I've collected that data, I've plotted it all together, and what's happened is that actually we've got two distinct groupings here, and together you might think, it looks like it's going up from the bottom left to the top right, and it's positively correlated. But should we be graphing all that data together? If I just looked at this data, how correlated is that? If I just look at that data, how correlated is that? Okay, so you've got to take each case with a pinch of salt and knowing about the context. Let's have a look at another example. How about this one, right? You could potentially have a couple of bits of data that make it look like it could be correlated. However, if I get rid of these might just be, they might have been written down incorrectly, recorded incorrectly. Okay, if I take those away, and suddenly the data's not correlated at all. Let's have a look at this one. This one looks like maybe the data's kind of funneling up in that direction. Okay, from something that's like not very correlated to something that is pushing up that way. But the moment I get rid of like those two bits of data, just two bits of data, the correlation doesn't appear to be there at all. Okay, so you can see that sometimes a graph can be misleading. So you've got to be careful with analysing scatter graphs and inferring bits of information that actually aren't there. So all three of these bits of, all three of these graphs, when we've been talking about this approximation to an elliptical shape, none of these fit the bill. Okay, you might be thinking, well, I could draw an ellipse around it. I could draw an ellipse around any shape, really, couldn't I, right? But you're looking at the whole data, so really it's like circle down here and a circle up there, rather than an ellipse that carries the whole lot. Now, next question. What do I mean by causation? Right, see if the person next to you knows what that word means.
One variable that causes another variable.
Okay, perfect. One variable causes another. Okay, so this idea that just because you draw a scatter graph and just because it looks like it's quite strong positive correlation means, that must mean that one is causing the other to increase, or one is causing the other to decrease. That is a poor inference, really, okay? That's not necessarily the case. And that's why we come up with this stock phrase, which, if you take anything away from today's lesson, is the most important thing as a sentence to remember. And that is that correlation does not imply causation. Just because you've drawn a scatter graph, they look correlated, doesn't mean that one causes the other. Okay? So make sure you've taken a note of that if you don't know it already, because that could potentially be an answer for your exam. Right? Okay, so there is this great website which looks at these. It's called Spurious Correlations. You can just Google Spurious Correlations, and there's some excellent examples in there. I've got a few to show you. So, for example, this one is the divorce rate in Maine in America against per capita consumption of margarine. So what you can see is actually these two things correlate pretty closely. But does that mean that because the divorce rate is going down, that the consumption of margarine is going down? Right? Just because they're correlated, does that mean they're causing one another? Here's a total revenue generated by arcades and computer science doctorates awarded in the US. Oh, they're correlated. Math doctorates awarded and the uranium stored at US nuclear power stations or power plants. Okay? So, in actuality, you can draw these graphs and, you know, people could draw graphs of scatter graphs and go, look at this strong correlation that I found. They must be connected. When in actuality, maybe they're not at all. Now, in each of these cases, there is a percentage that's been attached here for each of these correlations. 99.26%, 98.51%, 95.23%, all very high correlation figures. So where does this figure come from? How do we calculate a way of giving a correlation, a percentage, a certain value? And that's where the product moment correlation coefficient comes in, otherwise abbreviated to PMCC because it's quite a long title, and it's otherwise known as Pearson's coefficient. Okay. Now for the data that you had for your scatter graph, okay, what I'm going to first need you to do is to work out the mean for your x's and the mean for your y's. Okay? So could you do that for me first? So remembering our notation here, okay, so x bar represents the mean, and using the summation notation is the sum of x's divided by n. Add them all up, divide by how many there are. So we should get two figures, 4.625 and 3.5. Now what I would like you to do is if you could add that as a data point to your scatter graph, preferably using another colour, or you could use, if you've used dots, you could use a cross, or if you've used crosses, use a dot. Add that as a coordinate to your scatter graph. You should find that the data point is kind of slap bang in the middle, right? As you probably would expect. Now, can you remember when last year, when you were doing S1, and you were first introduced to the standard deviation? Can you remember kind of how you calculated it, like from the very start? People shaking their heads. Can't remember that. Can you remember we kind of did it as looking at, we were trying to find the average distance away from the mean. So we subtracted the mean from each of the data points, and we found the average of those distances, because we had to square them, because they're all some were positive, some were negative. We had to square them to make them all positive, and then we divided through by n, and then square rooted back. Can you kind of remember us doing that? We're going to do a similar thing here, okay? So I'm going to divide this graph up into 4 sections, okay? And what I'm going to do is I'm going to look at the vertical and horizontal distance between each of these data points and the mean. Now, I'm going to multiply those two figures together. So what I'm going to do is I'm going to find the horizontal distance. So this has an x value, and I'm going to take away the x value of the mean. And I've got a y value, I'm going to take away the y value of the mean. Now this would be a positive value multiplied by a positive value. Now the reason why I might multiply them together is to get an idea of how far away these points are from the mean. Okay, so the larger that figure will be, the further they will be away from the mean. Okay, so each of these data points, I will get a positive value for each of those when I multiply the x distance by the y distance, because it's a positive times a positive. If any data point was up here, however, if I had a data point there, when I did the x value take away the mean, I'd actually get a negative number. The y value would still be positive, so I'd have a negative times a positive. So all of those values would be negative. I haven't got any up here, but they would all be negative if there were. Down here, I've got a negative times by a negative. So all of those would give me positive results. And over here, I'd have a positive times a negative. So all of these would give me negative results. So If I then got all of those together, all of those numbers, and added them all together, okay, I would get what is referred to as SXY. It's kind of like the sum of the product of the x's, y's distances. Okay, so we've got SXY. So the sum of each of the x's, take away their means, times each of the y's, take away the means. Okay. Now, if I added them all together, what do you think I would get? Because I've got a few up here. I've got 3 up here. I've got 4 down here. They're positive numbers. I'm adding on more positive numbers. And I've got this one number here, which would get me a negative result. It's not going to really make much of an impact. Now, if I add them all together, I'm going to get what would be a large positive number, because the majority of my data is in region number 1 and region number 3. I'm adding positive numbers together. Brilliant. It's positive correlation, isn't it? So it makes sense. If I had most of my data up here and down here, I'd get negatives and negatives. So I'd add them all together, I'd get a negative result. That makes sense, because it would be negative correlation in that case. And if they were all over the shop, right, then I'd have positive values cancelling out with negative values, positive cancelling out with negative, and so they pretty much add up to something that's close to 0, right? Which is neither positive nor negative. So that would probably represent no correlation. So that kind of fits. That kind of makes sense. Okay? But there's a problem. Isn't there always a problem? Okay? Nothing is ever that simple. Because if I had just some data, much like the data we've got there, much like the data you've got on your bit of paper, and this goes from 0 up to 10. Now, would you say that this data is any more correlated than if I just change the scaling? So is one more correlated than the other? No. However, if I did this calculation with that one, the value that I would get would be much, much larger, because my distances would all be multiplied, right? So I might get a value here of, I don't know, 10. Over here, I might get a value of 1,000. So if I'm comparing 10 against 1,000, you might go, well, 1,000's bigger, isn't it? So that must mean they are more correlated. But clearly they're not. So the scaling has an issue here. So there are some problems. No allowance has been made for the number of data items, okay? So if I just added an extra bit of data, just one more bit of data to this, suddenly my value of adding them all together might balloon, right? I'd get a much larger value just from one data point being added. No allowance has been made for the spread within the data, so slight differences of being here or here might cause a difference. And probably the biggie of the bunch, no allowance has been made for the units of x and y. So just changing the units shouldn't change the correlation. So this isn't quite right. So we need to do some scaling. And this is how we scale it. So we say that our sample product moment correlation coefficient is given by this formula. And what's great about this, those SXXs, SYY, can you remember, like, thinking about those from last year, right? SXX we kind of dealt with. What they do is they scale it so that they give you a value between -1 and 1. Okay? Where +1 is perfect positive correlation. So if you got a value of 1, they would be in a perfect straight line, going from bottom left to top right. If you got -1, then that's perfect negative correlation. And 0 is no correlation whatsoever. And so anywhere kind of like between that, you've got varying levels of correlation. So 0.8, 0.9, 0.95, these are getting stronger positive correlations. Okay? Now, that's lovely. What are the SXX and SYY, you might ask? Well, they look like that. Okay, so SXX is the sum of these guys, the xi minus x bar all squared. You might remember that from when we were calculating standard deviation last year. This is the one for the y's. Okay, it's like the sum of the squares, we called it. But remember that they were quite difficult to work with in practice, so we utilise instead a formula that looks like this. Now conveniently, right, this is in your formula booklet. Do not think you've got to learn it, okay? But we do need to know how to use it. So you've got the sum of the xy's can be done into shorthand using sum of xy, sum of x, sum of y, and n. Okay, rather than using that, the sum of the sum of the squares of the x's, sum of the squares of the y's. So this is on page 6. So if you've got your formula booklet with you, it's a good opportunity to have a look and see where it is. So page 6, bottom left, you've got the SXX, SYY, and SXY formulae. Top right, you'll see the product moment correlation coefficient, Pearson's coefficient. So it gives you the full formula, okay? What you will notice is that the formula in the top right is subtly different to the ones in the SXX, SYY, etc. down here, okay? Now, don't be put off by that. It's just that in this one in the top right, they're using x bar, y bar, whereas in the bottom left, they use x bar is sum of x over n, okay? So they've broken it down into using summations. So they're subtly different, okay? But don't get put off by that. Right, now, on your calculator, thankfully, you can work out all of these bits of information. Those of you who have the Casio class whiz, you're going to find this a little bit easier, okay? So we're going to try it with this data set, okay? So the data set we had before. I'm just going to write it down for my benefit. 1, 3, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 3, 3, 5, 5, 6. Right, okay, now. Okay, so, on the class whiz, okay, you need to go to menu, and then, just like reminding myself, can I just grab yours? Go to menu, and then you need to go to number 6, statistics, and then number 2 for y equals a plus bx, okay? And then input the data. So on this guy, on the older Casio, number 3, okay, when you go into mode, then number 3 for stat, then it's a plus bx, number 2. You'll get up a table and you need to fill in your x's and y's, okay? Okay, so once you've inputted your data, is everyone happy with that stage? Okay, press AC, that's on both calculators, okay? Now, for Class Whiz, you need to go then Option, and then, does it say something like 2 variable calc? That's the one to click on. And you'll get a whole range of all the bits and pieces you need. If you're on this one, we need to go to Shift, then number 1 to go into Stat. Okay. Now the summation bits are in number 3. So it will give you sum of x squared, sum of y squared, sum of x, sum of y, sum of xy. It's all in there, okay, that you need. You can also go through Shift 1 and then number 4 to get n and the mean if you want to use the other formula and the y bar. Okay, so x bar, y bar. Okay. So what we're going to want is these values. So could you, with your calculator, find me these values? And then we're going to try and plug them in to the formula. So those of you with the Class Whiz can see this all off one screen, which is really convenient. Right, once you've got those points, the bits of data, the summary statistics, could you plug them into the formula? So I've written up on the board, but it's also on page 6. Okay. Now you might want to do it in like stages, so you don't need to put it all into the formula in one go. Figure out what SXY is, then SXX, SYY, and then plug them in. That might be a lot easier. This isn't the same as the top right one, because I've written it in the summation formula using the ones in the bottom left. That's why it might look a little alternative. But it's only because the X bar, Y bar bits.
Yeah, it's just confusing why there's no over n on.
Because both numerator and denominator have been also multiplied by n. So that it'd be like I could get back to the one that they've got by dividing both top and bottom by n. I would get the n here. I would need an n squared there to have x bar over n times y, sum of x over n times sum of y over n to give me the x bar, y bar. Really, I need the n squared there, wouldn't I? Yeah. Okay. So it's just an alternative way of figuring it out, but it gets you precisely the same value. Right. Now, what you should get is 0.963 to 3 sig fig. Now look what I've done, right? Now this can help you break this problem down into pieces. Some of the squares of the x's, some of the squares of the y's, some of the xy's, okay? And then plugging them into the formula. You might find it easier that way than trying to do it all in one go. Remember, S2 is all about eking out those little 1 markers where you could potentially make slips. Because the grade boundaries are so high, we've got to think about where can we get this right every single time without fail. Now, you've also, as Dan was pointing out, another shout out there, as Dan was pointing out, you've got a button on your calculator that can give you this end result. So there's no reason, if you were given the data, should you not be able to check your working. So on the Class Whiz, with your data still in the calculator, you can press Option, and then I believe it's number 3, Regression Calculation. Okay, regression calculation will give you 3 values, an A, a B and an R. The A and the B we are not on to using yet. We will be. The R value is the one you want. If you're on the regular Casio, then press Shift 1 and then there's an option for REG, if memory serves. And then you can get R that way. Right, so what we're going to finish off with, I'd like you to have a go at some questions from the MEI textbook that's on your table for Stats 2. Remember, you can be given a question where you're not given the data. In all likelihood, you won't have the data there, and what you'll have to do is you'll have to figure out the value of R given the summary statistics. So you might be given those, and you need to show that you can substitute them into the formula to calculate R. Okay? So that's how we can work with the product moment correlation coefficient.